All right, so hello, microscopists. So, had a lot of requests for this. Well, I've had a lot of requests for lots of videos, and I know it's been a long time since I've put something out there, so I apologize for that. But we're going to tackle PFIB lamella prep today. And actually, funny story, I tried to do this once already, and I got to the end, and the final thinning went terribly. And I'm sitting there thinking, well, I can't really use this video because this doesn't show a good result. Because this is one of the things I found with the PFIB is there's some inconsistency. So if you're seeing this video, then you know that the final result was a good one, but doesn't always necessarily turn out that way. So we're gonna hope for the best here and see what we get. So I have the system under vacuum, as you can see right here with the little icon of everything. And this is our sample over here. So I can maximize one quad by clicking on it and then selecting F5. Is this pizza slice here. So this is actually 111 silicon. So if I double left click on it, I can drive so we're over that. And then if I click and drag upward with my scroll wheel on my mouse, so I don't have the beams on yet, but I'm going to drive this up to close to 4 millimeters just to get us in the ballpark. So the 111 silicon, this is actually the standard that we use when we are we're preparing the test sample to shoot the 200 kilovolt resolution spec on the Themis. So that is, again, viewing silicon along 112 zone axis, where you can see the dumbbells that are separated by 78 picometers. All right, there we go. So we'll go over all that here in a little bit. All right, so a few things to do before we start here. Click on your E-beam quad, stage, beam shift reset. Do the same thing for the I-beam quad. I-beam scan rotation, I like putting this at 180. Again, this is a matter of preference, but especially when you do the lift out with the manipulator, that makes things a lot easier. You want to make sure mags coupled is checked, okay? It doesn't matter which beam you have selected, that will be good to go. And we are ready to turn on the beams. So I'm going to hit beam on. One of the nice things about this system is that, whoops, do I need to hit? Let me hit wake up here. There we go. Okay. Yeah, so when you do a load cycle, it should automatically turn these on. The reason that these were actually cold was because I had told it to go to sleep without actually doing a load cycle. So when it does a load cycle, it will automatically do this. So without turning on the heating to the GIS. So, but yes, good thing I checked this. Yeah, so these heat up pretty quick. Anyways, again, when you hit the wake up button, that turns on both beams and it turns on the heating to the GIS. Anyway, all right. So I'm going to start at 2 kilovolt, 6.4 nanoamps for my E-beam. Okay, and let's move to the edge of the sample over here. Okay, so you can see a bunch of bullet holes here. So this is where I've already cut a few samples. So we're going to use this to help us do a few things. We're going to use it to help set the height and to tune the image. Okay, so once you're focused, hit the UFO question mark button. And we're a little bit short of 4 millimeters, so we'll move to 4 millimeters. And then we will mechanically set the height. So tilt to 26. And then use your stage Z to bring that. I'm using this side of the trench here to bring that back to the middle. Okay, then tilt to 52, and it's basically perfect. You could scooch it down just a smidge here. All right, we'll do one more iteration. You'll also notice the appearance of because I'm doing the screen capture using the Black Magic input director. This looks different, the screen, than what you would see normally, but aside from that, everything else is functionally the same. Those of you who are using this tool at the RSC, and those of you not as well, you'll notice like this kind of looks a little strange, but that's why. All right, so we can scooch it up now just a smidge. Yep, there we go. All right, so we have established eucentricity. I've made up a word there, eucentricity. So what we can do now is tune our electron beam. So we find direct adjustments, click crossover. We can use the zoom to change the size of the spot. So this is close, but we can get this a little better, I think. Okay. We'll turn on the lens modulator. Okay, and there's really not much movement here. Again, if you're trying to minimize shifting of the image, so again, like if I use the crosshairs here, there's really not much. If I throw this off here, as you can see now it's going left to right. So if you pull the crosshair that goes vertically side to side, right, you're adjusting the side to side movement, okay? If you pull the one that goes horizontally up and down, you're adjusting the up and down movement. Okay, but we're good there. All right, and then we're gonna stigmate. So I can use this corner here. I can turn on reduced area if I want. So your dwell time here will be different depending on what you had it set to. It will go back to what you had for reduced area. So we use 3 microseconds. And then I'm just using my stigmator knobs to stigmate my image. So stigmate and focus. Perfect. Okay. And there we are. All right. So now we can talk about aligning the sample. So because this is 111 silicon, this nice straight cleave edge here, this is actually corresponding to a 110 direction. So if I make the cut direction of the lamella from left to right, my beam direction is going to be 110. Okay. Now if I want it to be that, that's perfect. Okay. But if I'm interested in making a sample where the view direction is instead 112, I have to rotate the stage 90 degrees. Okay, so my cut direction actually is parallel to the cleave edge. That will end up giving me a beam direction that goes from left to right, which is actually 112 direction. Okay, so this is already, vertical. Okay, so what I can do though is I want to make this horizontal, right? So if I can go to stage, align feature, I can click and drag, and then I want to align this so it's horizontal. Make sure you do stage rotation here, okay? And then click OK. And we should see, there we go, okay? So we can see now this is going from left to right, okay? So when I cut the lamella this direction, my beam direction is going to be perpendicular to the cleave edge, and that is going to give me 112 direction, okay? All right, so now I set eucentric here, okay? So, my eucentricity should be good within the vicinity here. But what I'm going to do anyway, because these have already been kind of adulterated, is I'm going to come over kind of a little bit a ways away from where I already, cooked the sample. And that's perfect. I got something I can focus on here. So this is silicon with a rather thick layer of chromium. The reason I put the chromium on, that was part of a test depth for another sample, but I wanted to, throw that in there at the time. All right, so we'll take a snapshot and we'll draw a pattern. So I do have a preset for this, but let me draw it manually anyway. So go to patterning, select rectangle, click and drag, PT depth E-beam, and we'll do 10 by 1.5 by 1. Okay. And then again, I have a shortcut for this on my system, okay, on this system. So the shortcut is just make sure you have the E-beam quad activated and click preset 1, okay? Does the same exact thing. Let's put in the platinum. I'm gonna turn off this, I don't want this on. Okay, there we go. And we'll go ahead and get started. So this step is gonna take about 3.5 minutes. So if you have something else you need to do for 3.5 minutes, go right ahead. While that's happening though, I'm gonna kind of, blab on here for 3 minutes to kind of discuss some of the nuances and intricacies and frustrations of using PFIB to make lamellas. So the use of xenon as the ion source in the PFIB changes the dynamic of a lot of things, okay? So the thing you have to keep in mind is when you're using xenon, which is a gas-based source, versus gallium, which is a liquid metal ion source, you do have a really profound difference between the two ion sources in terms of what's called the brightness of the source, okay? And so that translates into a big difference in the ultimate beam size that you're getting when you're preparing the samples or you're milling, right? So you end up with beam sizes with the xenon fib or the PFIB that can be 2 to 3 times what you would see with the gallium fib, all other factors being the same, okay? So, that's one of the things you have to keep in mind, right? Is your milling in general tends to be less precise with a PFIB than with the gallium fib. The use of xenon also has some other issues. So, I mean, one of the things that's kind of empirically known just with the interactions of ions with matter is that heavier ions tend to cause more morphological instability and roughening of like a surface than we would get. So xenon, of course, is a heavier ion than gallium is, right? So we have that to kind of contend with as well. We do also sometimes see issues with the ion beam assisted platinum with the xenon because you are incorporating xenon into the platinum, and xenon, as we all know, is a noble gas and does not like to bond with other things. So what we sometimes see happen with the ion beam assisted platinum is we tend to, or sometimes anyway, we can get porosity, bubbles, cracks in the fib deposited protective layers. And that is obviously not good, right? Because if your sample quality when you're doing your final thinning, right, to a large degree, or at least to an important degree, right, can be impacted by how solid that protective cap is. Okay, so again, these are all things that make PFIB lamella prep far more challenging than gallium fib lamella prep. Okay, so we will keep that in mind. Okay, all right. So we're almost done here. Okay, take out your platinum, delete your pattern. There we go. Got a good looking strip. All right, so now I'm going to change. I haven't done any live ion imaging yet, but I'm going to change my ion beam settings to 12 kilovolts and 0.33 nanoamps because this is what I'm going to use for doing the strap. Okay, so I'm going to change those, and then I'm going to tilt to 52 degrees. So we'll see how close to eccentric this spot is, which was probably 0.5 millimeter away from where we actually set it. Okay, so a little bit low, so we'll bump up the Z here, okay, and put it back, okay, and there we go. Okay, so it looks like already my stigmation with my E-beam has kind of gone out a little, but not uncommon. All right, stigmation doesn't stay good forever. All right, so we're going to put the platinum in here. Okay, and then we are going to go live with the I-beam. Drop my dwell time here, okay, and use my beam shifts to center my sample. Where are we here? Okay. Okay. Okay, you can focus really quickly here. Just leave that alone. All right. So again, I'm going to go back to the rectangle. Now I'm going to do PT dep I-beam, and I'm going to do 10 by 1 by 1.5. Okay. Now, those of you who are familiar with PT dep with the I-beam are going to notice, you're going to say, Nick, that's a really high current density, okay? So my actual current is about 465 picoamps, okay? So this is, that means my current density is around, 46 picoamps per square micron. And that's a really high current density. But what I find empirically is that I can use a higher current density when my voltage is lower, okay? And what that ends up doing is it actually ends up giving me an enhanced deposition rate. So I find that I can lay this down in, a minute and a half, what would normally take about like 3 or 4 minutes with a more kind of traditional current density at a higher voltage, okay? So again, a more traditional ion beam current density for doing PT dep is around 10, I think 6 to 10 picoamps per square micrometer. So I am exceeding that by about a factor of 4.5. You can see we're getting a nice thick strap going down here. Again, I do have a preset for this. Okay, it is preset 1 here for the I-beam quad. I'll show you this when it's done. Again, I made these presets, so these are not the default for those of you on a different system. Like I actually made the presets here. Okay, but you can see, right? Preset 1, there you go. All right, so now I am going to take out my platinum to let me tilt, and I am going to tilt to 57 degrees. So I'm going to over tilt by 5 degrees. We're going to go back to 30, and I'm going to use a low current here, just 30 picoamps. So what I'm going to do right now is a technique known as blind milling. Okay, so what this is where you use a low current. So in our case, let me mag out just a smidge here. Okay, you use 30 picoamps here as just a setup image. Okay, then what you do is you draw your pattern. So I'm going to draw a regular cross section, and I'm going to make this pretty big. So silicon, we'll go 20 by 10 by 10. Okay, and now we're cutting from the top with the 180 scan rotation. So I want the thick end down here. So I'm going to rotate 180. Okay, and now again, I have the exact same pattern here as a preset. Okay, so again, if you don't believe me, right, boom, preset 2, there you go. Okay, so then I'm going to keep this here. Now, if you look at the time, it says 42 hours. Okay, now we don't have 42 hours to do this, right? We'll be here forever, or close to 42 hours anyway. So we need to use a higher current. So I'm going to go up to 60 nanoamps. Now it's only going to take me a minute and a half. Okay, but 60 nanoamps, my beam is really big. Okay, so in order to deal with that, I have to give myself a pretty wide margin of spacing here. So I'm going to move this pattern so it's about 1.5 strip widths above it, above the strap. Okay, so right there. and then we will go ahead and start. Okay. Some things to note with the silicon pattern. So I had to make some adjustments to it from the, the state that it was delivered when we got the machine. So one of the things in particular was this parameter called the overlap. I had to make this a lot larger than it was in the default file. So the default file, the overlap was 50%, and the results we were getting were terrible with that. So what I found was by increasing this to 85%, I ended up with a lot better results. Okay, particularly in terms of the sidewall roughening and the smoothness. Okay. You can't change the file inherently, like this silicon file. You cannot change unless you're in like the admin account. But you can, like once you draw the pattern, I'll show you this when you're done, you can manually change it just for that run. So I'll show you this here in a second. You can see though we're not hitting the strap, right? The strap is being maintained, which is perfect, right? We don't want to touch the strap at this point. All right, so you can see, right, I could, if I wanted to make this say 70, okay, I can do that just for the, but if I change the file, you see this went to like grayed out. If I change this back to silicon, it's going to go back to what it is in the file, okay? All right, so we're going to tilt now to 47, and we're going to do the same thing from the bottom, but now I have to go back to 30 picoamps and get my setup image so I can do my blind milling again. All right, so let's rotate the box now, 0 degrees. And same thing, I'll put this box in the middle, give me about 1.5 strip widths. Perfect, okay? Go back to 60 nanoamps. And there we go. So when you're live ion imaging while you're milling, I mean, it looks pretty noisy because your ion to E-beam current ratio is really high. So one of the ways you can help with that is to average, right? So you find the little filtering icon and you turn on averaging. So I have it set to 4. You can set it to any number you want. Usually 4 is pretty good. Okay, but again, you can see, so we're milling the other side of the strap, and we're, again, not hitting the strap, right? So again, we really shouldn't be hitting the strap at all during this initial portion of the prep, okay? We shouldn't be really getting into the strap until we do the final thinning. All right, almost. So when this is done, I'm going to delete this pattern. We're going to go to a different pattern. All right, I'm going to go back to plus 5 degrees. So the reason for the over tilting and the under tilting is to do 2 things. So one is it tapers the lamella toward the bottom, which is going to make it easier to undercut. The other thing that it does is it helps to reduce the wearing down of the PT strap, okay, by doing this. All right, so we're going to go to cleaning, and we're going to go 20 by 1 by 5. And again, we want the thick line at the bottom, so we do 180, and then I'm going to place this so it's like just up against the strap. So you see this is actually some redep here. I'm going to put this right next to it, and then I'm going to stretch the top up manually, okay? Again, right? Preset 3, okay? Draw it right there. Center it up. and bring it back. Okay. So now I'm going to drop down to 15 nanoamps, and I'm going to turn on SPY mode here. So basically, every time it does a slice, it's going to take a snapshot, so we can see the sidewall here. So we want to make sure we're not cutting in to the strap here. Okay, so you have to activate this and then unpause the E-beam. Okay, so we're getting there. We're getting there. Perfect. All right. So gonna do the same thing now from the bottom. We'll go 47. Again, I'm gonna go down to 30 for my setup shot. Okay. Can probably scooch this. Oops. Okay, we'll leave it right there. Okay. 15. And away we go. So now this is a little trickier now because we're cutting the back side here, so we can't actually see it. Keep my finger on the stop button just in case, things get out of control. Looks like we'll be okay though. Yep. Beautiful. One more slice. Perfect. All right. So now we're going to undercut. So the magic angle for the undercut is 7. That puts our ion beam at 45 degrees relative to the trench. And once again, I'm going to use 30 picoamps for my setup shot. Okay, now I do. So I have a preset for this, but I'm going to show you this anyway. So rectangle pattern. So draw one rectangle, okay? Silicon. Now make the depth, you can make it 5, something really high here, okay? So this one on the right, basically, we have to clear out this entire side of the strap, okay? Now if you click and then do Control-C, Control-V, you paste the same one, okay? So then I'm going to make this bottom one. Okay, so I want the height, about 1.5 microns here. And then I want this to extend all the way over. And then I'll do Control-C, Control-V again to put my other one here. Okay, so you notice I have overlap in the corners, right? You want overlap here. Oops, come on, where are you? Okay, now with this one on the side, again, I'm lining up the edge about with the edge of the strap, okay? This guy you don't want too close to the top, okay? And you can make it about, I don't know, 70% of the way from the top edge. As far as the depth, you have to kind of keep in mind, like, what are you trying to do with the sample? Like, and a lot of the time we're only concerned about right near the surface. So you can see this is probably about, about halfway into the trench. So I'm going to leave this as is. And I'm going to switch now to 4 nanoamps to do this. Okay, you could do this also at a nanoamp. It's a little less aggressive. Okay, so one of the things I'm going to do here, I'm going to use a little trick just to make sure that my beams are coincident. So I'm going to turn on reduced area, then unpause, and boom, looks good. Okay. So now I know the images are coincident. Okay. Let me put this back, and you want to set your pattern to parallel so it does all of these at once. Okay. And away we go. So now this is where unpausing the I-beam image comes in handy, so you can actually see it eating away. Especially at 4 nanoamps, I would be conservative with this box here. Don't get this too close to the top or you'll end up cutting it through. Oops, let's turn off spy mode. All right, so we're almost there. All of a sudden, my contrast brightness knobs aren't working for the I-beam. I don't know why. That happens sometimes. All right, we're getting close here. Yeah, that's weird. Sometimes it happens. You have to adjust it for the E-beam, and then it works here. It's like a glitch with the system. All right, so you can see here, this is the bottom, still not cleared out. So it's close though. All right, and that is nice and clear. There we go. All right, so we could do another step with this if we want. Let's tilt to 0. Now just to show you, I also have a preset for the J cut, okay? Preset 4, okay? There you go. Same idea. Let's tilt to 0. All right, so do we want to run one more step on this side? We can take a measurement here and see how thick the sample is, about 2 micron. Yeah, okay, I'm gonna leave it alone. We're gonna lift it out as is. So you could do a post-cleaning step to this side if you want, but I'm just gonna leave it alone for now. All right, so we're ready to lift it out. So make sure you're live here. We'll go to 100 picoamps. Gonna insert our easy lift. Gonna insert our platinum. Okay, and we want our easy lift right here. Okay, so you want to go down with the Z. So if you keep the Z, or if you put the 180 rotation for the I-beam, your easy lift is going to come from the top. Okay, so you should see it come from the upper right here. There it is. All right, so once it gets about 10 microns away, I'm going to drop the speed down to 1. I do have a preset for the weld, but I'll draw it anyway. So click and drag on a rectangle, PT depth. We'll do 2 by 2 by 0.5. Okay, and again, preset 4. Okay, same thing. Let me just put this out of the way for a minute. Okay, so those of you at home might be saying, my easy lifts don't look like this, and you're absolutely right. So this is an easy lift that I sharpened. You are correct. They don't come like this. All right, so sneak it down here. Come a little bit, move it forward so it's kind of Okay, that's good. It's not as blunt here as I would have liked, but this should work okay. All right, so we'll put it there. Put the weld right there, and we'll run it. And hopefully this works here. Yeah, so we're seeing the glue come in there. So you don't have to be touching the lamella. You can have a little bit of a gap, and then the PT will kind of fill the gap in. So, and this is plenty. We're good. So you don't have to run this pattern to completion. You can just run it. All right, so now I'm going to switch to 1 nanoamp. I'm going to leave the image, and I'm going to do the release cut. So again, rectangle, silicon. Can do 1.5 by 5 by 5 here. And again, I also have a preset for this, which is 6. Okay, I just call it release cut, but we can modify this here. Just stretch it out. And there we go. Okay. All right, so we should see, there's the shadow of the cut through. So we should see this once it's through. And we saw the lamella kind of bounce down a little, which is good. It means it's loose. All right, perfect. Stop. Switch back to, and we'll go to 30 here. Okay, switch to my easy lift control. And then I'm going to hold Z positive till I get the sample out of the trench. And then I'm going to put it in park. So park, go to. Retract. PT depth retract. All right, and now we can head to the grid. So I have the grids over here, and I have in positions 3 and 4. So on my system, I have stored stage positions for these. Okay, so I'm just going to navigate to them. Otherwise, you'd have to just click on here and navigate. But let's go to grid 4. So I'm going to double left click on grid 4. It's going to drive over. Let's see where we are here. Okay, so here we go. So we have a brand new Ted Pella brand OmniProbe grid. Okay, so this is the way I loaded this in. This is the one post we're seeing. So this has like a notch. So I have it here in the center. I'm going to focus it. Then I'm going to switch to the E-beam. Okay, so you can see this is a little bit high. So I'm going to move this down. The other way to do this, of course, is we can, do a manual adjustment here. So center it. Oops. We're focused, so let's hit the UFO button. And we can tilt to 26. See the one dot, so one post. All right, so it's pretty good. I'm going to move it down just a little. All right, so I'm going to go back to 0 here, and we're going to do a couple of tweaks here. So we want to check a few things with the grid. We want to make sure that the grid is, we're looking at it basically straight on, parallel, so it's not pitched forward or back. So it looks really good at 0. Just to show you, if I was at -2, right, see? So you can see the front side. So you don't want this, okay? So you have to compensate for this till it goes away. So we can see like 2 degrees the other way, no good. So if I do 0.5 degrees, okay, not bad, but still a little bit there. So 0 degrees, right? So usually you have to pitch away from 0 a little, but here it worked out pretty well. The other adjustment you need to make is that the grid is straight from left to right, okay? So if it's not, you want to do stage align feature and then click and drag left to right, and then stage rotation horizontal, click OK. So it didn't even move anything because it was already at 0. All right, so what we have to do with this grid now is a little more pre-prep, okay? So I'm going to go back to 52. So we have to do a couple things here. So the surface of the grid is pretty rough right now, okay? If we mount the lamella on the grid as is, we're probably going to run into an issue with shadowing of the grid, okay? So what I mean by that is parts of the grid are going to end up blocking the line of sight when the TEM or the lamella is imaged in the TEM, okay? And we don't want that. So what we're going to do is we're going to first cut a hole in the front side of the grid, okay? So the front side is the bottom side here in the I-beam, again with the 180 rotation. So I'm going to draw a rectangle, make it 40 microns wide by approximately half of the grid width, which is 10, and we'll do 12, I'm sorry, and then 10 for the depth, okay? We want to center this up on the post, and then we're using a very high current, so 0.2 microamps, and then we'll go ahead and hit play. And again, for whatever reason, my contrast brightness knobs are not working for the I-beam here, but that's okay. So what this does is it's removing all the material here. So when I go to mount the lamella, I'm not going to have anything in front of it, okay? All right, so let's tilt back to 0. And we can see the nice hole that we put in the grid. Okay, I'm going to leave the current here. All right, so now I'm going to cut now through the grid the other way. So you can see right here, this cut face I made. I'm going to move the box so it's just below the dip here. And then I'm going to stretch the top so it goes through the back like that, okay? And then hit play. So what we're doing now is we're cutting a shelf. So we're going to cut a shelf here, and we're going to make this flat. Get a drink of water here really quick. All right, let me stop this. I'm going to just stretch or compress the top down. So this should be nice and smooth once this is done. So you'll see what I mean here in a minute. All right, we're getting there. Almost. We can run this a little bit longer. All right, we're good. We can stop it. All right. And then I'm going to drop my I-beam current back to 0.1 nanoamps. So what we have done now is we have created an ideal grid geometry. Okay, so basically all this is cleared out, and now this is a slanted shelf. So this part of the shelf is the highest and this is the lowest. So we're going to mount the sample here on the front. So now nothing is going to be in front or behind the sample when we put it in the TEM. Okay, so that ensures that we have good line of sight. All right, let's insert our easy lift. Let's insert our platinum. Okay. I do not recommend using 100 microns a second. I've already had problems with people crashing probe tips doing that. All right, switch to 1. And I'm going to draw my preset 5, the same one I used for the easy lift weld I'm going to use here. Get a focus. Okay, so I want the sample along this edge here, so I want it back basically like about like yay. Okay, so basically right against the front there. So now it doesn't need to be actually touching the grid here. I can have a little bit of a gap. Like that. That's perfect. Okay, I can move it up a smidge. There we go. Okay, perfect. Put that there. So this you can put along the lined up with the edge, and there you go. So we're welding this corner right now. Sometimes it's, you can see the weld going down, sometimes you can't. This one I would recommend, it's set for 0.5 microns. I would just let it go the whole way just to make sure that you get, plenty of deposition there. You can see it there building up, so I guess we can stop it. Let me mag out here to, okay. All right, I'm gonna keep the same snapshot here, not take a new one, just move the box over and run the same thing for the other side. All right, so doing good so far. So now the question is, can we final fin the lamella and have it look good? So again, if you're seeing this video, the answer is yes, although it hasn't always turned out that way. Yep, so you can see it over here. All right, that's good. Okay, so now I'm going to switch to 1 nanoamp. I'm going to draw a rectangle right here. And we're going to cut the easy lift free. So the easy lift's pretty skinny right now, so this should be gone in no time at all. Make sure you cut it all the way through though. Leave a nice, clean, easy lift cut face for the next person. There we go. Okay, I can move it away, stop it. All right. I'm not looking at the I-beam, I'm just going positive Z, just a ways, and then I can put it in park. There we go. Retract. Retract platinum. Okay, so what we need to do now for the final thinning, and this is the heart of the lamella prep, we need to drop our E-beam current down to something a lot lower so we don't worry about contaminating the sample while we're imaging it during final thinning. So if you drop, I like to use 0.2 nanoamps here, but we're going to have to redo the alignment. So, okay. Looks good. Okay, turn on the lens modulator. little side to side. Okay, there we go. All right, focus and stigmate. Okay, there we go. All right, it's good enough for now. Okay, so now we're at 0 degrees. We're lucky is normal incidence for the E-beam, so we don't have to really do any, extra math here. If we were at -1 degrees for this, that we had to pre-tilt in order to get the grid parallel, we would have to take that into account, okay? So I'm going to tilt to 54. So I'm going to go, that's 2 degrees of over tilt, okay? Again, if you were -1 initially, that would be 53 you would put in there, okay? Okay, and there we go. All right, so I'm going to stay at 1 nanoamp here. Okay. All right, I'm going to pause this, turn on reduced area, and I'm going to use this part of the grid here to help me tune the image. Just focus it well. Looks good there. Okay, make sure your lamella is focused, and we're good there. Okay, so I'm over tilted by 2 degrees. So the first thing we're going to do is cleaning cross section. This is going to be most of the lamella. The final thinning is the cleaning cross section. Okay, so we're cutting from the tops. So we're going to use 180 rotation. We'll do 5 for the Z. The current's pretty high. And I'm going to be kind of aggressive here, okay? So what we're going to need to do here is we want to cut into the strap until we see the nice E-beam, I-beam layering, okay? We can turn on spy mode here, and we'll go. Let's bump this up. So this is one of the things that's tricky with this. So there's, when the I-beam platinum goes down on the E-beam platinum, it's, there's a point at which there's good overlap, and you have to make sure you cut far enough into the sample to find that. If you don't, then, that can be a problem with your, final result. So again, with this first cut, you can be a little more aggressive. I am cutting through the whole width. I will start tapering it once we get down to, once we go to the back side. And as you can see here, I still have this discontinuity in the strap, so we have to cut into it more. We may not get far enough into it on this first cut, but that's okay. So when you're doing the cleaning cross section like this in particular is where having that 85% overlap comes in handy. So if you don't have that high enough, then this is where your sidewalls end up looking not as nice as they should. But so far so good here. All right, so we're getting close to this being nice and uniform here. We're not really seeing the E-beam yet, though. We're starting to see it, though. All right, I'm going to stop it here. Make sure I don't cut through the welds. Okay, I can start to see it forming, though. So, all right. So we're going to tilt now 50 degrees. I'm going to keep the, let me take a snapshot here and look. Okay. Let's see. Do we want to go to, yeah, we can keep this. All right, so what I'm going to do here is so this is in principle 2 degrees of undertilt. I'm going to undertilt another degree. The reason I want to do this is I want to make sure I can see like the side wall here slanted toward me. In fact, I'm going to go another half degree here. So what I find here with this is you have to be a little less formulaic. Like you can't just be plus or minus 2. If you do that, then you're going to end up, especially from the bottom here, probably over milling the sample, which you don't want to do here. So I'm going to be really conservative with the box placement here, and I'm going to make sure it's kind of off the bottom pretty clearly, right about that. So this is definitely, this is staggered across, so I'm not cutting the whole way through. Okay, we'll leave it there. Okay, there we go. So now we're cutting the back side here. Once this step is done, I'm going to drop down to the next current, which is 0.3 nanoamps. And you see we haven't really lost any height of the strap yet at this point, which is good. So you don't want to be losing strap height yet. Really not at all at 30 kilovolts. All right, let me do, well, I'm going to stop it here. Okay, let me take a snapshot. Yep, perfect. So you can see how much it actually chewed into it, okay? All right, so I'm going to go back to 54. And I'm going to drop down to 0.3. And I'm going to, again, turn on reduced area. And again, make sure my focus and stick, they look really good right now. I just like aligned it, so there's really no need to do much here, but okay, there we go. Still with the cleaning cross section. We'll do 8 there, 0. I'm going to drop my depth to 4. So I'm going to just be right over that projected sidewall. So right about like that, okay? All right, there we go. And there we go. So I can start to see the E-beam coming through, which is good. Things are looking promising so far. Although I said that with the last one, it didn't turn out well. So famous last words, right? And this looks good. We're seeing that nice E-beam layer there. Nice continuous, solid looking platinum. So far so good. So ideally we want to cut into this till we see the platinum for the E-beam reach kind of a max thickness. So you can see it's still getting thicker as we cut into it. Right, so we haven't probably hit the peak yet, but that's okay. We got time. Okay, very good. All right, so let's try 50 and see how it looks from the bottom. All right, so this looks like we're basically edge on. So let's do 48 degrees here. Okay, so now I can see the sidewall. So all right, I'm going to drop this down to 7 and 0, and we'll leave it at that. What some people actually do is they will rotate the stage every time they do a cut, so they're always looking at the side that they're cutting. That obviously is very effective, but time consuming. So I don't usually do that. I guess if you had a super critical sample, maybe something you could consider doing, but all right, looking good so far. And we'll do one more line from the bottom here. I'm going to stop this prematurely. Okay. All right, we'll go back to 54. So it looks like we're going between, so 54, and then it's like, actually, believe it or not, it's like minus 3.5 on the bottom, what I've been doing here. All right, so we'll drop to 100. Okay, so that's actually pretty good thickness for this. All right, so same thing, reduced area. Looks good. All right. Cleaning cross section. We'll drop it to 6.5, 0.3, and 4. Rotate down. Okay, and we will, let me make this 3.5. Okay, so what we're going to try and do here is, again, we're trying to cut into this until we see, we want to see that E-beam strap there kind of reach a maximum. Now we could actually probably turn this off and just live image this now, because our current ratio is a little more favorable. Okay. So I'm using my shifts to shift the E-beam. we go. All right, so we're seeing the strap here reach like a peak here, which is good. Excuse me, taking a drink of water here. All right, we're getting there. And we still haven't lost any height on the cap, so which is good. All right, when this line ends, I think I'll stop it and we'll cut from the other side. All right, let's take a look here. Okay, looking good. Okay. Again, going to be conservative from the back side here, so we'll leave it about there. All right, there we go. So this should be the last step at 30 kilovolts. And then we're going to drop down to 8 and then drop down to 5. For 8, we will still use the cleaning cross section. For 5, we will go to the rectangle. But so far so good, about as good as I could have expected it to this point. Moving along. Yeah, everything looks good. So have a nice continuous solid platinum layer. So you want to try and do as much damage as you can at 30 kilovolts because your milling is just more precise. Your curtaining is less, like your roughening is less, and you know your sputtering yield is higher. So everything's just more. Now your damage layer is thicker, so you have to leave some material left, right, to remove the damage. Let's see here. No, I'm gonna let it ride here. We'll let it ride for one more cleaning cross section. That looks good. All right, let's take a look here. Nice. Okay, so we're probably around 300 nanometers thick. Okay, so all right, so we're gonna go 55. So we're gonna go plus 3 degrees from the top. I'm gonna drop down to 8 kilovolts here. Okay, so your image at 8 kilovolts is not gonna look very nice, but this is, you know, part of the deal here. You can stigmate and focus. You can also do lens align here. If you come here, turn on L2 modulator. So this is like lens alignment. You're trying to minimize the movement. Okay, looks all right there. All right, cleaning cross section again. We'll go 5.5 and by 3, and then 180 from the top. We'll manually mess with the dimensions. So I'm gonna again keep it kind of off the side or off the top there, and we'll leave it about, yeah, about like yay. Okay, let's go. Ignore this. It just means the current is a little bit deviated from expected. So particularly at 5 kilovolts, you want to do as little milling as possible. Empirically, it's known that as the voltage goes down, like the roughening gets worse, the curtaining and whatnot. So one of the reasons I don't use 2 kilovolts on this machine is at 2 kilovolts, the roughening is really bad. So if you compare the damage from 5 kilovolt xenon to 2 kilovolt gallium, it's not much different, okay? I think the xenon might be a little bit thicker, but I doubt you would really notice the difference, like in terms of the lamella quality. So that's why I stop at 5. I go from 30 to 8 to 5. At 8 kilovolts, the curtaining really is not terribly bad. So That's one thing I'm seeing here. I'm actually going to proceed with previous line. All right, so yeah, we're getting a nice spot here that's getting cleared out, so we should be okay. You can see down here it's a little bit rougher, but we don't care about that usually. You only care about the top part here. So one thing you can do though is you can execute the patterns again. So if you want to, redo a step here, just redo a line, you can. But I'm going to let it ride here. We got this nice area here. This is perfectly fine. All right, so let's take a look. Okay, so we'll go 48. All right, let me go one more. So it actually looks okay. Let me go 40, and we'll go 47.5. All right, there we go. 0, 5 degrees. We'll manually change this to 0.3. Take another snapshot. Okay. And there we go. Ignore. So now again, we're cutting the backside and we can't see it. So, so what we're going to look at here, primarily, we're going to monitor the strap here. So the strap should start to wear down, which is, not unexpected. We want there to be like still a little bit on here before we head down to 5 kilovolts though. And we should see the strap start to light up as it gets, thin, which is what we want. Okay, so you can see it's going down here. All right, let me stop it there. Okay. Actually, it was a little more aggressive than I would have thought, but all right, we'll leave it there. All right, so we're going to drop to 5 kilovolts. And 10 picoamps, so really low current. We're also going to tilt to 57. Okay, focus and stigmate here. All right, so we're gonna go now to the rectangle. Go 4.5. Leave the Z alone. We're gonna monitor this manually, so we'll put it right there. Pull this down a little. And there we go. So what we should be seeing is the silicon up here lightening up here as we're getting thinner. Keep in mind, especially at 5 kilovolts, like the beam is outside of the box, right? It's not confined at all to just the box. So which depth we got? 0.2. So you can see we're chewing through the bottom, but not a problem. Again, that's the trick, right? You can just double left click and that pulls this up. So you can see all about your pattern. So I'm going to run this to, let's see. I mean, I've definitely, definitely got rid of the 8 kilovolt damage layer, right? So that's not an issue here. I'm going to run it to 0.3. And then I'll stop it and we'll do the back side, and that will hopefully complete everything. I don't have a lot left on there, but I should have enough to get us thin. All right, so I'm going to go kind of conservative here. That's 46. I'm going to keep the box. And we'll go 4. So I'm placing the box well below, like this is the top of the sample. So I'm putting the box well below that, okay? Because again, I'm trying to avoid chewing into it, okay? All right, I'll leave that there. Yep, there's the platinum lightening up, which is good. So basically, you can run this till you have just like a little bit of platinum on the surface, right? Just a little bit there. This one definitely turned out a lot better than the the one I tried before, though. so I'm very happy with that. Again, it goes back to the inconsistency of PFIB, right? It's just the way it is. There's a lot of inconsistency. Chewing through the bottom there, but otherwise we're looking pretty good. Just a little bit there. I'm going to stop it before we chew all the way through it. That's a chromium coating on there, so. But all right. All right, let's stop it there. All right. So there we go. So let's take a look now. If we can measure it edge on here and see This is definitely one of the better samples I've made with PFIB. All right, so it's probably 100, sub 100 nanometers here. You can definitely get these, thinner than this. We're at 0 degrees, unless I'm not tilted the right way. I mean, we can try -1 here and see. Okay, so that probably, gained us a little bit here. Yeah, so it's definitely, so we weren't quite looking at the right angle here. -1.5. Okay, that probably is a little bit thinner still. Yeah, so it's probably about 50 nanometers thick. So at least maybe thinner than that even. But all right, so there you go. So there's the PFIB lamella prep. So it can indeed be done. So you have questions, comments, things you'd like to let people know about PFIB lamella prep, please put them in the comments. So and hope you find the video useful. All right, thanks everyone.